A wise person once told me, give a person an H and they'll heat transfer for a day. Teach a person to Nusselt number and they'll heat transfer for life. So today we're going to talk about computing our own H via Nusselt numbers for flat plates. So before I sort of tell you what equations exist and how to use them, we'll take a step back and we'll talk about laminar versus turbulent boundary layers. What they look like, how boundary layers might transition between the two, how they might appear over flat plates, and how laminar versus turbulent flow might affect the heat transfer coming from a plate. So we'll know how important it is, whether the flow is laminar or turbulent, and that will inform, what Nusselt number equation we end up using. Then we'll recap what sort of arguments and what sort of definitions of parameters go into Nusselt number calculations. So we'll talk about arguments and definitions. Spoiler alert, we're going to be basically talking about Nusselt number, Reynolds number, and Prandtl number, and what parameters go into those things. Then I'm going to drop a big old chart down on you. And this chart is basically going to have equations for Nusselt numbers. But, hypothetically, we could say, all right, there should be maybe one Nusselt number function to rule them all. But instead, practically it's easier to sort of break up these equations for Nusselt numbers into a set of simpler equations that each have specific ranges of particularly Reynolds number and other conditions that they apply. So we'll have a chart with multiple equations for these Nusselt numbers and sets of criteria that tell you which equation to use. And the criteria that we'll use is do we want a local or an average Nusselt number? And if this distinction between a local or an average Nusselt number is something that seems a little foreign to you, take a look at the previous lecture that we've uploaded, where I sort of clarify what that distinction is and why, under what circumstances each one would be useful in your heat transfer problems. The second thing would be laminar versus turbulent versus what I'll call mixed, where under some circumstances part of the plate could be under laminar flow and part of the plate could be under turbulent flow, and you need special consideration when that's the case. And then the final question that you need to ask yourself is, what is the heating condition of the plate? Is it a constant surface temperature or constant heat flux? So basically, if you ask these three questions about your system, then you can sort of follow the rows of the chart to pick out just the right Nusselt number equation, and then use Reynolds number and Prandtl number to then compute your Nusselt number, use your Nusselt number to compute your H, and then move on with your life. It turns out that the fluid properties that go into the calculation of Nusselt number, Reynolds number, and Prandtl number, those fluid properties often depend on temperature. So because these fluid properties depend on temperature, but all of that fluid might be at slightly different temperatures, right? We're going to have a different temperature for the fluid close to the surface versus far away, upstream versus downstream. Strictly speaking, there's not one single temperature that applies to all of this fluid. So strictly speaking, these fluid properties are all, they're non-homogeneous over the whole system. So I'll basically say, hey, like, can we describe a single set of fluid properties so we can actually go ahead and use these correlations? So, what temperature, so because these fluid properties depend on temperature, what temperature to use. And spoiler alert, it's basically going to be called the film temperature. And I'll more precisely define that once we get to this point in the lecture. Then finally, we'll sort of bring together all of these concepts and actually apply them with an example problem which is the flow past what's called a hot strip anemometer. An anemometer is a device used to measure the speed of fluid. So basically, because heat transfer depends on Reynolds number, and Reynolds number depends on how fast that fluid is flowing, you can actually use heat transfer to estimate what fluid flow is. So you basically put this little device, it's sort of like this heated flat plate with a couple little arms sticking on it. The flow goes past this flat plate, and based on how much heat that flow carries away from the flat plate, you can infer what the velocity of the fluid is that was encountering that plate. So rather than having like a little pinwheel or a little windmill or something like that with moving parts, or a pitot tube where you need to have like fluids moving around in response to velocities, you just stick a little plate in there, measure how much heat you need to keep that plate at some prescribed temperature, and that will give you all of the information you need to infer fluid velocity. So it's a pretty cool device, useful in, certainly in mechanical engineering and things like that, but it can also be used within, for example, like chemical processes or other things like that to basically infer fluid speeds. So this is where we're going with today's lecture. So let's get started with this discussion of laminar versus turbulent boundary layers. So here's a secret of the universe. Turbulent flow over a flat plate is inevitable if the plate is long enough. So let's look at a flat plate. Last time we said, hey, let's say I have some fluid that is encountering this flat plate, and prior to encountering the plate, it has some uniform velocity. Maybe we'll call it V infinity or something like that. And if we looked at the hydrodynamic boundary layer, we said, hey, this fluid that comes in stops once it gets to that plate, and some of that flow basically gets redirected up. There's this boundary layer that basically grows, and the fluid transitions from the free stream velocity just outside the boundary layer all the way down to zero velocity right at the plate. So the boundary layer is basically this transition between free stream velocity and zero velocity down at the plate. It turns out that for flow past a flat plate, there's a transition between, you can have laminar boundary layers and you can have turbulent boundary layers, and it turns out that there's a transition where the flow at the upstream part of the plate often starts out laminar, but after a certain point, after a certain critical point at the plate, this laminar boundary layer grows and grows and grows and gets too big, and eventually that flow always gets tripped to turbulence. So there's a critical point, and then downstream will be turbulent. So, even, no matter what fluid you're dealing with, no matter if you like really tried to keep this plate ultra smooth, everything like that, there will be some point, some X downstream of which, no matter what, the flow becomes turbulent. And basically these turbulent boundary layers, we end up with a lot of fluid that's mostly moving in one direction, but also has a lot of swirling chaotic mixing and all of that stuff. So a lot of times if we have heat transfer from a plate, that we get this laminar boundary layer that grows for a while, then there's some critical point after which the flow essentially trips itself into turbulence. Now, in some cases, this critical point downstream of which it might become turbulent, you might have a plate that is so short. You might have a plate that is so short that the whole thing, that it's laminar throughout. So, you could have a case where plate is shorter than the x that would transition to turbulence. And in that case, you might have a laminar boundary layer over your whole plate. It's also possible that you can have a flat plate where you put a couple of nubs at the beginning, and these nubs essentially trip the boundary layer into turbulence right at the start. So in that case, you might have a turbulent boundary layer throughout your entire plate, even if, without these turbulators, the first part or maybe even all of the plate would have been laminar. So this is the deal here. We could have a plate where the whole thing is laminar. We could have a plate where the whole thing is turbulence if we trip it into turbulence at the beginning. We could have a plate where part of the plate is under laminar flow and part of the plate is under turbulent flow. So a lot of times we might need to consider, what is the length of the plate, or what is the position of the point that we're investigating in relation to this critical point on here. This critical point, you can basically compute by looking at what Reynolds number the flow transitions to turbulence. So flow, except in this case where we have intentionally tripping it to turbulence, left to its own devices, flow transitions at a critical Reynolds number. And it's a critical Reynolds number based on x. So at a critical Reynolds number based on x, we have rho v infinity x critical divided by viscosity. So there's some critical Reynolds number that corresponds to this critical x right here, where the flow transitions to turbulence. And it turns out that this critical Reynolds number is equal to 5 times 10 to the 5th. So this 5 times 10 to the 5th Reynolds number, for example, if you knew your v infinity, rho, and mu, this 5 times 10 to the 5th would give you some physical distance at which, would give you the information you needed to correspond to the physical distance at which you expect it to transition to turbulence. And that might help do I have a mixed boundary layer? Do I have a fully laminar boundary layer? And then, of course, you don't really need to consider this Reynolds number based transition to turbulence if you have something that intentionally trips your plate into turbulence right at the beginning. Well, why do we care so much about turbulence? Well, you can imagine if I have all of this swirling and mixing fluid, the swirling and mixing can enhance heat transfer from the surface. But the swirling and mixing also basically creates greater mixing between V infinity and the slow fluids down here. So this turbulent boundary layers tend to be thicker. So they tend to be thicker, but they also tend to be more homogeneous as well in terms of mixing cold and hot fluids. And it turns out both of these factors impact the heat transfer from the surface. So laminar versus turbulent boundary layers end up being super important towards computing Nusselt numbers and eventually H's, or the heat transfer coefficients associated with this convection. So let's consider this qualitative description of boundary layers when we're talking about the Nusselt number equations for laminar versus turbulent flow. All right, so we just talked about laminar versus turbulent boundary layers. Now let's talk about arguments and definitions for Nusselt number, Reynolds number, and Prandtl number. So this is a quick recap from what we talked about last time. Last time we said that convection coefficient, let's say h. So let's say we were dealing with a local one. Our h of x, we said, hey, this is going to be a function of x, the thermal conductivity of the fluid, the fluid density, the velocity of the fluid flowing past the plate, as well as the viscosity and specific heat of the fluid. So, this is basically going to be a function of all these things. We can do the non-dimensionalization to basically show that h sub x times x over k, which we could call a local Nusselt number sub x, is basically a function of rho v infinity times x over mu and mu times Cp over k of the fluid, which we could alternatively say, hey, this is our Nusselt number, this is our Reynolds number sub x, and this is our Prandtl number. And we could do similar arguments for the averaged Nusselt number, h bar sub L times L over k is equal to nu bar sub L, which is going to be a function of rho v infinity L over mu and mu Cp over k. And this would basically be a function of Reynolds number sub L and Prandtl number. Not the product of these two, just that's a comma separating them. So it turns out that, people did a whole bunch of experiments to essentially characterize both local and average Nusselt numbers. And rather than trying to break out, one function for them all, they instead said, hey, let's just sort of break this up into a bunch of domains. The domains we talked about earlier. Are we talking about a local versus average Nusselt number? These are going to be two different functions from one another, and I'll clarify what these functions are once we fill out the chart. We're gonna, rather than sort of have one function that attempts to apply for both laminar or turbulent flow, again, like these characteristics are going to be so different from one another that it's more convenient to have two separate functions that apply to the two separate conditions or the two separate locations on the plate. So instead of having single functions, we'll just sort of break up these functions into separate domains, and it turns out that basically the form that pretty much all of these functions are going to take is going to be some Nusselt number, it could be an nux or an nu sub L, is basically going to equal some constant, we'll call it constant number 1, times Reynolds number to some power, some constant, and it depends on whether which one you're talking about, what exactly these constants are, times Prandtl number to some different constant. So pretty much all of these functions, based on these three regimes or three different conditions that we could have, pretty much all of these functions are going to be of the form some constant times Reynolds number to some power times Prandtl number to some different power. So all these functions are basically going to take this form. They're all going to have arguments of Reynolds number. It might be a Reynolds number sub x for an h sub x. It might be a Reynolds number sub L for an h sub L, where they have slightly different definitions. But basically all of these functions are going to take this form. So let's build ourselves a chart where we have several versions of this function for each of the conditions. So so you could take a moment now, if you're, we're going to fill out this chart, or at least fill out some of it. Take a moment now and kind of fill out a sheet of paper with rows and spaces as follows. So, pause the video and fill it out. So what are we going to do? We're basically going to fill out this chart. And we're going to have, different parts of this chart essentially correspond to the different questions that we're asking here. So the first question that we want to ask ourselves is, hey, are we dealing with a local Nusselt number or an average Nusselt number? So for the first part in the chart, we're dealing with just a local Nusselt number. That is basically h sub x times x over k. And for this bottom part of the chart, we're dealing with an average Nusselt number that we're calling nu bar sub L. That's h bar sub L times L over k. The second question we ask ourselves is, are we dealing with laminar flow or turbulent flow? And so for here, the local Nusselt number will have laminar and turbulent. And remember, that's Re sub x is less than 5 times 10 to the 5th. And here it's Re sub x is greater than 5 times 10 to the 5th. For the average Nusselt numbers, we might, it's not just is the point where it, so for local Nusselt numbers, it's basically, is the point we're investigating laminar or the point we're investigating turbulent. For these average Nusselt numbers, we basically need to ask ourselves, is the entire flow laminar? And in which case, Re sub L would need to be less than 5 times 10 to the 5th, where even the most downstream point of our plate still needs to be laminar flow if we're going to say, is there an average Nusselt number where the entire flow is laminar? And then for the second one, we'll sort of say, we'll look at two cases, one where the entire flow is turbulent, where we have this, this case where we have a little turbulator at the start of the plate, or we have a mixed boundary layer. And we'll basically have one equation where there's sort of two slightly different versions of it. In the mixed, we have some of the plate laminar, some of the plate turbulent, but we're just saying we're not interested in the details of what's going on if we're talking about an average Nusselt number. We're just saying, hey, in aggregate, how much heat is flowing out of this whole thing, or related to like average surface temperatures and stuff like that. So this is basically what we're building out here. And then for the third question that we need to ask ourselves is, are we dealing with a constant surface temperature or a constant heat flux? And it turns out we get slightly different Nusselt number equations for those two things. So here, constant surface temperature, constant heat flux. Then for this one, we'll say constant surface temperature, constant heat flux. For here, we'll have a constant surface temperature, and here we'll have a constant heat flux. And then it turns out for this one, it doesn't matter. Either is fine. You can use the same Nusselt number correlation for either case in this final condition where we have some mixed or fully turbulent. And then in this very last column, we'll put some restrictions on when you can use some of these equations. So this first one only works when Prandtl number is greater than 0.6, as does this second one. Prandtl number needs to be greater than 0.6. For this third one, Prandtl number needs to be between 0.6 and 60. As does this fourth one. For this next one, Prandtl number just needs to be bigger than 0.6. And then for this last one, Prandtl number needs to be between 0.6 and 60. We also have a couple restrictions for Reynolds number on some of these. For this turbulent one, Reynolds number needs to be greater than 5 times 10 to the 5th in order for it to be turbulent, but it also needs to be less than 10 to the 8th where, you know, it can't be too turbulent. So, you know, it turns out that the correlation kind of breaks down in terms of its accuracy once we get too turbulent a flow, and that's also true for this. So in this column, we're basically going to fill out a bunch of equations. You know, I'm going to do it right here, but of course you can fast forward through this part of the video if you don't want the tedium of me doing it. So this one's Nusselt number sub x equals 0.332, Reynolds number to the 1/2, Prandtl number to the 1/3. This one's 0.453, Reynolds number to the 1/2, Prandtl number to the 1/3. This one is 0.0296, Reynolds number to the 4/5, Prandtl number to the 1/3. This one is 0.0308, Reynolds number to the 4/5, Prandtl number to the 1/3. We're now in averaged Nusselt number regimes. So this average is 0.664, Reynolds number to the 1/2, Prandtl number to the 1/3. This one is equal to 0.680, Reynolds number to the 1/2, Prandtl number to the 1/3. And of course, for these ones, we're doing Reynolds number sub L. And then this last one is a little bit tricky. It's equal to this thing right here, 0.037 times Reynolds number sub L to the 4/5 minus what I'll call A, and then this whole thing times Prandtl number. This whole thing also times Prandtl number to the 1/3. And A basically has two possibilities. A is equal to 0 if turbulence tripped at x equals 0. So it's, you know, A is basically this quantity. A is equal to 0 if we're in this case where the whole thing is turbulent, or A is equal to 871 if the transition at at the normal critical Reynolds number sub x, right? So it's basically A is 0 if we're in this case, A is 871 if we're in this case. And I just want to clarify, A is not an area. A is just a placeholder variable to sort of have one equation kind of work for either entire turbulent flow or a mixed boundary layer for averaged Nusselt number. All right, so there we have it. That's our chart. Now, on to the last question we were going to talk about, which is, hey, you know, all these fluid properties depend on temperature, so what temperature do we use, right? We anticipate that, you know, we're going to have some temperature, some surface temperature that's going to be different from the free stream temperature, and if we're doing the constant heat flux case, that surface temperature isn't even going to be constant, right? So surface temperature could be non-constant across the surface and is definitely going to be different from the free stream temperature up here. So we use what's called the film temperature. So evaluate at what we call the film temperature. And this film temperature, we'll call it TF, is essentially an average of the average surface temperature and T infinity. So it's basically, you know, take your surface temperature, take your T infinity, add them up, divide it by 2, and this bar over TS is, you know, if if I had the constant heat flux case where my leading edge is going to be at a different surface temperature than my trailing edge because I have constant heat flux, not constant surface temperature, I've averaged the surface temperature and then averaged that average temperature with the average heat flow. So it's like, I heard you like averages, so I'm averaging your averages to get a film temperature. And this film temperature is what you use to evaluate your fluid properties. So for example, if we need these fluid properties, right? We need these fluid properties to plug into these things for Reynolds number and these things for Prandtl number and this for Nusselt number. So we're going to need these fluid properties, and a lot of times when you look up fluid properties, they vary with temperature. So if you're going in like engineering toolbox or whatever to look up what the properties of air or water or ethylene glycol or whatever are, you might need a sense. You might say, hey, what film temp am I going to need to evaluate these properties? I forgot one caveat for this one. We have a restriction on Reynolds number for this one as well, and that's basically Reynolds number needs to be in between 5 times 10 to the 5th and 10 to the 8th as well. So there's restrictions on Reynolds number here. All right, so that's what we have here. So take a moment now, pause and ponder. What is the difference? What is the difference between or I guess not between Nusselt numbers. Let's say, what is the difference between H sub x evaluated at x equals L and H bar sub L? So what is the difference between these two things? And think about what is the difference between them qualitatively, and what differences might they have in terms of evaluating these things in terms of the chart. Well, hopefully you've had a chance to pause and ponder. What H bar sub x is saying, hey, what is a relationship between surface temperature at some particular point, at one particular point on this surface in T infinity, and the heat flux that flows through that point. So, so I might, this H sub x evaluated at x equals L is saying, hey, what is going on just with this one point at the very downstream most point on this surface, right? So, here's, let's say, x equals L right here. I might want to investigate a relationship between this point's temperature and T infinity and the heat flux flowing out of the plate at this point. So that's what H sub x at x equals L does. H bar sub L is the average of all of that junk coming from the plate up, from starting with the plate's leading edge and going all the way through x equals L right here. So in general, we might think about things, heat transfer coefficients tend to be better when, or higher when the boundary layer is thin compared to when the boundary layer is thick. So almost always H bar sub x at x equals L is usually less than what the averaged H bar sub L is, because the averaged H bar sub L takes into account this region at the leading edge where there's more effective heat transfer between the plate and the fluid, whereas just evaluating what the local one is downstream. So usually H bar sub x evaluated at x equals L is going to be less than H bar sub L, because the average one is incorporating the more effective heat transfer at the leading edge of the plate, whereas the local one is just what's happening at that single point downstream. But your purpose for using them might be very different. You might say, hey, what is going to be the hottest point on the plate? Some point right here, or what's happening on average for the whole plate. And that would inform which one of those you use for your analysis. All right, so let's move forward with our example problem. let's say I have this device. It looks like a little rectangle, and both both the top and bottom surfaces are heated. There are these little arms that kind of hold it up. I'd hold it up. Let's say we know some various lengths and widths. So there, it has some width W, some length L. And let's say this device, it has like a little thermocouple in it, like a little temperature sensor in it, and also it has like heaters kind of embedded as wires, electrical resistant wires throughout. So basically, there's electrical current running through these wires. It heats up the whole thing, and there's also a little thermocouple in here that basically says, give me just barely enough power to maintain my surface for this whole device at some constant Ts. And then there's some flowing past the whole surface, and before this flow encounters the flat strip right here, so we have flow essentially flowing over the top and over the bottom of it. This flow, which I'll call U infinity right here, is between, let's say we anticipate it being between 1 meter per second up to 50 meters per second, and it's air. So this might be the sort of problem that you might be given, and you might be asked to find out, hey, how much, what heater power would be maintained in order to keep this constant surface temperature given these parameters right here. So let's just say Q heater is equal to, I don't know. And let's say we wanted to maintain this constant surface temperature at 35 degrees C, and we knew that the flow coming in, the T infinity of the fluid coming in, we knew was going to be equal to 25 degrees C. And then let's say our width was equal to 50 millimeters, and our length was equal to 20 millimeters. All right, so let's say we had this device. This might be the kind of problem that you're given. So basically, how much electrical energy do I need to keep this double-sided strip at this temperature given these flow characteristics, and do that, and given that it's air flowing over it. Well, you can say, hey, I'm gonna need, I anticipate there's going to be basically convection, and this is convection over a flat plate, so I'm going to need some properties of air in order to do this calculation. So you can basically look up. You want to look them up, and we have a constant surface heat temperature, or a constant surface temperature at 35 degrees C and 25 degrees C air coming in. So we want to look it up at the film temperature, which is the average of these two. So that's going to be 30 degrees C. So we look up properties of air at 30 degrees C. You can do it on like Engineer's Toolbox or whatever. And it turns out that Cp is basically equal to 1.0049 times 10 to the third joules per kilogram Kelvin. Viscosity is equal to 1.846 times 10 to the minus fifth kilograms per meter second. Thermal conductivity of air at this temperature is equal to 2.624 times 10 to the minus 2 watts per meter Kelvin. And then you can use all of this, you can use all these parameters to basically calculate the Prandtl number, which is equal to 0.71. And then you can also look up the density of the fluid, which is 1.18 kilogram per cubic meter. So all of these are properties that you can basically look up for air at this particular temperature. So this is all of the information that we're going to need to figure out how much heater power I'm going to need to supply to this to account for all of the cool air that encounters the warm plate and gets carried away. And if we're looking for the worst case scenario, the maximum, the most intense heating that we're going to need, we're going to do so given the sort of fastest velocity, right? So the faster the fluid, the more heat it's going to be carrying away. So we're going to basically say, hey, what's the heater in this worst case scenario? Where we have the fastest possible moving fluid. All right, so that's the problem setup. We're also going to assume that the system is in steady state. All right, so here's all the information we need. How can we do it? So we can basically do conservation of energy, and we can basically define our control volume around here and apply conservation of energy to this control volume, and we can use the shorthand form accumulation equals ins minus outs plus generation. If we're in steady state, then we're not going to have any accumulation term. Heat convection is defined from the solid surface to the fluid around it, so we're not going to have any ins. The outs is basically going to be convection here, and the generation is basically what's going to be for our Q heater here. Right? So this is going to be Q dot heater. So our outs, that's going to be from convection. And because our outs are going to be from convection, we're going to need to use the characteristics of the flow and the properties of the fluid to calculate our own H. And from the calculation of our own H, that will then give us the outs here. All right. So what kind of H? So what H will we need? Well, we're looking to aggregate total heat flows. We're looking to relate T infinity and our surface temperature. We're not interested in the details of what's happening at this point in the plate or this point in the plate or this point in the plate. We're just saying, hey, how many watts are coming out of the whole plate? I'm just lumping that whole thing together. So if this is the kind of H that we'll need, because we're sort of lumping the whole system together and not investigating single points, that informs using an average H. So in this case, we're using the average H, so that's going to be an H bar sub L. So we're basically going to say, hey, what is the average heat transfer coefficient over this whole thing? And that'll allow us to relate the surface temperature, T infinity, and this whole heat flow flowing out. All right. So this is what's we're going. So we take our conservation of energy. We're going to need to use this average H bar sub L. So it ends up being, we had 0 for accumulation. We had no ins. Our outs is going to be Q dot convection. And then our generation is going to be Q heater. All right, so take a moment now, pause and ponder. Does Q dot convection equal the following? Is Q dot convection going to equal the following? Does it equal H bar sub L times L times W times Ts minus T infinity? take a moment now, pause and ponder. Is this statement true? Close, kind of. It turns out that this would be true if only one side of the plate were convecting, but these hot strip anemometers basically have flow both over the top and over the bottom, so we essentially need to double whatever we have here before we plug it in here. So we have convection both on the top and bottom surfaces, and that's why we have this factor of 2 here. So what does it mean? Once we plug this in here, we'll have our heater power entirely in terms of knowns once we've sorted out what h bar sub L is going to be. So as soon as we find h bar sub L, that'll give us all of the information we need for our desired heater power once we plug this in right here. So we are now on a quest to find h bar sub L. So h bar sub L, we can find this in terms of Nusselt numbers. So h bar sub L is basically going to be equal to nu bar sub L times the thermal conductivity of the fluid divided by length, right? So we can take the definition of Nusselt number and sort of reformulate it this way. So now, once we find nu bar, then that's all the information we need to find h bar, which is then all of the information we need to find our Q heater. So when we're thinking about this nu bar, we want to ask ourselves our 3 questions: local versus average, laminar versus turbulent versus mixed, and then constant TS or constant heat flux. Well, we can answer 2 of these right away. We know we're going to want the averaged quantity for this rationale right here, and we know we're dealing with the constant TS because that's what was described in the problem statement. So now we just need to ask ourselves, is the flow laminar or turbulent or mixed? Well, how do we go about doing that? We can calculate the Reynolds number. So we can basically calculate Reynolds number sub L, which is basically going to be what is the Reynolds number right at this very end point of the plate. And as long as, and if this point is turbulent, then we might be in a case where we have a mixed boundary layer. If this point is laminar, then we could pretty safely conclude the whole thing is laminar. So we'll calculate our Reynolds number sub L. That's rho U infinity times L over mu. You plug in, you plug in all of this stuff that was given right here, and I'll just kind of cut to the chase. That Reynolds number equals 6.4 times 10 to the 4th, which is less than the critical number of 5 times 10 to the 5th. So we conclude that the whole boundary layer is laminar. And there was no mention of any turbulators placed on the upstream part of this plate. So we can indeed conclude that the whole boundary layer is laminar. All right, so we have our Reynolds number. We conclude the whole boundary layer is laminar. That tells us which equation we're going to use for our Nu bar sub L. So we can bust out our chart. Local versus averaged. We want averaged. We concluded that the entire flow was laminar from our Reynolds number calculation. So average Nusselt number, entire flow laminar. From the problem statement, we have a constant surface temperature. So there we have it here. So that means we need to use this equation for here. We just check to make sure our Prandtl number is okay. We calculated our Prandtl number based on the fluid properties, and that's 0.71, which is indeed greater than 0.6, so we're okay. So we can use this correlation for Nusselt number, so we can plug in our Reynolds number that we calculated, our Prandtl number, and that'll give us all of the information we need for our Nu bar sub L. So To summarize here, our NU bar sub L from the chart is equal to 0.664 times Reynolds number sub L to the 1/2 times Prandtl number to the 1/3. Well, we just calculated our Reynolds number sub L, which we can plug in right here. We calculated our Prandtl number from the fluid properties earlier, so that's basically 0.71 that we calculated earlier. This gives us all of the information we need to calculate NU bar sub L. So we can now treat this as essentially a known constant. So we then take this, we plug it in right here. We can treat NU bar sub L now essentially as a known constant, which means we can now essentially treat H bar sub L as a known constant once we plug in K and L. We can now basically treat this entire thing as a known constant, which we can plug in here. I'll save you the time of actually plugging in those numbers. You can look at the notes I've posted online if you want to do so. But basically the power of our heater ends up being 3.93 watts, which, just to put things in perspective, it would drain 3 AAA batteries in about half an hour. So, you know, wouldn't be really practical to have a battery-powered hot strip anemometer, but it certainly wouldn't break the budget in terms of having it consume a lot of wall power. You know, this is about a 20th of what a typical laptop might use. So that's just some perspective right here. So hopefully you found this lecture helpful on finding your own H. You can now feel confident. I've empowered you. I've empowered you to become H creators, not just H consumers, by using the proper Nusselt number correlations. So hopefully this was helpful. Thanks for watching, and good luck with your studies of heat transfer. Take care.